We are talking about vectors today, and vectors are super important. They're going to be with us for the rest of the semester, and they're also the last bit of non-calculus stuff that we need to get in our toolbox before we can finally start doing some calculus in 3 dimensions. All right, so our definition of a vector is here. A vector is a quantity with both magnitude and direction. The best couple of examples I can think of for vector quantities are things from physics, like velocity and force. All right, so if you think about velocity, velocity in your car, it has both a magnitude, a size, and a direction, meaning that you're driving 60 miles an hour. That's the magnitude of your velocity. And then the direction of your velocity is the direction that your car is driving in. And then force, if you think about force, when you push something, there's the amount of force that you push with. That would be the magnitude of the force. And the direction, of course, is the direction that you're pushing in. So usually we represent vectors as arrows. So I'm going to draw us a simple little vector here. And that simple little arrow conveys a whole lot of information. It conveys the direction of the vector by which way it's pointing, and it conveys the magnitude of the vector quantity by its length. And for us, usually these vectors are going to be connecting 2 points, either in R2 or R3. So I'm going to give us a couple of points here. So you have a point at the tail and you have a point at the tip. So let's give these points some names like P and Q. And then the vector that's joining points P and Q, we call that vector PQ. And then we put this little arrow over the top to indicate that we're talking about a vector rather than a line segment or something. All right, so let's hop over to Geogebra and graph a couple of vectors and talk about them. So here we are in the 2-dimensional version of Geogebra. And Geogebra has this neat little vector drawing tool where you just need to tell it the start point and the end point. So I'm going to graph a vector that goes from 1, 3 to 4, 5. And it labels everything. I'm going to turn this off so we can see. Okay, so there's vector U. And notice what GeoGebra does over in the left-hand column. It calls this vector with this notation, this sort of tall parentheses notation, the vector 3, 2. And what that's referring to is the amount of X tick marks spanned by the vector. There's 3 X tick marks and the 2 Y tick marks that are spanned by the vector. All right, so if I draw another vector that does the same X and Y number of tick marks, let's go from 0, 0 to 3, 2. Okay. Notice that GeoGebra calls that the same vector, 3, 2. So GeoGebra seems to be implying that these are exactly the same vector. And it turns out that that's actually the case. A vector is completely defined by its magnitude and its direction. These 2 vectors have the same magnitude, the same length, and they're pointing in the same direction. So in math, we are going to treat these 2 as absolutely the same vector. It doesn't matter where the vector is located in the plane. So let's see if we can plot a third vector that's going to be equivalent to these 2 vectors. Okay, so I'm going to start over here in the second quadrant, let's say over at -5, 2. And to get an equivalent vector, I need to go in the same direction, 3 to the right and up 2. And sure enough, vector W, it says, is the vector 3, 2. This is another equivalent vector to vectors U and V. So we say that 2 vectors are equal if they have the same magnitude and the same direction. So here are 3 vectors that GeoGebra was calling the same vector. GeoGebra called all 3 of these the vector 3, 2. And that's GeoGebra's version of what we'll call component form of a vector. Our notation for component form will look slightly different but convey the same information. So ours will look like this. This is the same notation your book uses. We use those pointy brackets so that that doesn't look like a point. So pointy brackets means a vector, but it still gives you the X component and the Y component. So how do we get from those points to the component form? Well, just look at all 3 of these points. If you look at the difference in their X coordinates, they all have a difference of 3. So if I were to subtract 4 minus 1, 3 minus 0, -2 minus a -5, those all give you a +3 change in the X direction. And in the Y direction, we would do the same thing. 5 minus 3 would give me 2, 2 minus 0, 4 minus 2. That all gives me the Y component. All right, so let's write this down as an official formula. So if you're in R2 and you've got 2 points and you want to find the vector from x1, y1 to x2, y2, you're just going to subtract coordinate-wise. x2 minus x1, comma, y2 minus y1. Right, and that might sound familiar from your algebra slope calculating days when you would calculate y2 minus y1 over x2 minus x1. And when we were looking at those vectors, it probably had a little bit of a slopey feel to it, right? We were going up 2 y coordinates and right 3. That kind of had a rise over run kind of feel to it. So if you're in R3, your 2 points have 3 coordinates. Your component form is going to have 3 components. So you're going to subtract your x coordinates, your y coordinates, and your z coordinates. All right, so just be careful though, with vectors, you have to subtract in the right order. You have to subtract the end point minus the start point. All right, so let's get some practice finding component form of vectors. This problem asks us to find vector AB in component form, and that implies again that we're starting at A and ending at B. So when I do this, I need to subtract end minus start. I need to subtract B coordinates minus A coordinates. So we're going to do B coordinate minus A coordinate for the x's, and then the same for the y's, -7 minus a -5. And then just simplify arithmetic. -1 minus 2 is -3. -7 plus 5 is going to be -2. And there's our component form. All right, and then in 3 dimensions, we do the same thing. We'll just have a third component for the z coordinates. AB again, so we're going to do B minus A, -2 minus 2, 1 minus -3, and 1 minus 4. And I get -4. 1 plus 3 is 4, and 1 minus 4 is -3. All right, so let's take that last one over to GeoGebra 3D and see what a vector looks like in R3. The vector drawing tool in GeoGebra 3D is a little bit more clunky than the two-dimensional one, so I just typed these in with the vector command. So here I have the vector drawn from those 2 points that we calculated, and it gets the same vector as us, -4, 4, -3. And we can spin this around and look at it. I'm not going to make you draw vectors in 3D because it's a little bit difficult to do and difficult to grade. All right, so we'll just kind of appreciate GeoGebra's skills here. And then I also had it plot the vector from the origin with the same x, y, and z change. And again, you can see these are equivalent vectors because they have the same magnitude, the same length, and they're pointing in the same direction no matter which way I rotate. So in the next video, I want to talk to you about the magnitude of a vector.